10.4, we're going to start working with area and polar coordinates. So to try and help you wrap your head around what we're going to be doing, I've got a link, I think I posted on D2L, and it takes you back to our work with Riemann sums. Let me dial this down. Remember how we started approximating area underneath the curve? We started with a rectangle, and then we added more rectangles. And as you add more rectangles, the area underneath these rectangles became a closer and closer approximation to the area underneath the curve. So, okay, that worked out nice. In the limit, that turned into, the Riemann sum turned into a Riemann integral, and life was good. We're going to do the same kind of thing, except now that we're working with polar equations, instead of having a rectangle here, we're going to have a little wedge. And the area of that wedge is going to be close to the area of a circle, a little part of a circle called a sector. Now that area might be familiar. It has a formula that we've dealt with before. The area is 1/2 pi r squared theta. Theta is your angle in radians. So that's going to become like our d theta. Is that little slice? That's going to be like a d theta. The area of the sector is, kind of reminiscent of the area of a triangle somewhat. We put that together, we end up with this formula. Area is theta over 2 times r squared. Eventually, if you toy around with this enough, you'll end up with this formula for your integrals. Area in polar is going to be the angle alpha to beta of 1/2 r squared d theta. So r is some function of theta, and we're going to integrate with respect to theta. We just have to substitute these things in, and we're good. Now, let's start out with kind of a simple one, and it's a good reminder or good heads up on what some of these things are going to be like. Now, fortunately for us, r equals 7 cosine theta. This is just a circle. I think its center is going to be at 3.5 on the x-axis. We're not even going to get all of that. We're just going to get a little part of it. And I'm sorry I don't have this one graph for us, but let's just do some of the mechanics here. So instead of r squared, I can write 7 cosine of theta squared. And my angles are going to be here to here. It's going to be your alpha, that's going to be your beta. And let's put everything in. So the area between this curve and the x-axis, between this curve and the pole, I guess I should say, and by this I mean the pole, for these two angles is given by this. A equals 0 to pi over 6 of 1/2 of 7 cosine of theta squared d theta. Okay, great. Let's square this out. 0 pi over 6. 7 squared is going to be 49. 49 divided by 2. Let me take that out front. 49 over 2 times cosine squared of theta, d theta. I was mildly distressed when I was grading a few exams and people wanted to integrate that like a polynomial term. It doesn't become like cosine cubed of theta over 3 or sine cubed of theta over 3. Instead, what we have to use is a double angle formula for this one to kind of get rid of that cosine squared part. Does anyone remember what that cosine double angle formula would look like? Or half angle? Go ahead. 1 plus cosine of 2 theta all over 2. Now that 2 in the denominator can come out in front, so it's going to give me 49 over 4 times the integral from 0 to pi over 6 of 1 plus cosine of 2 theta d theta. I'll keep this 49 over 4 out in front. 0 to pi over 6. The antiderivative here is just going to be theta. And now we have to think a little bit about this. When you integrate cosine, what do you get when you integrate cosine? Sine. So it's going to be sine of something, sine of 2 theta. But I also have to worry about that theta. I'm not just integrating cosine of theta, I'm integrating cosine of 2 theta. If I were differentiating, the chain rule would say I'd end up multiplying by 2. But you're integrating. So that's the opposite of this. So if you're integrating, instead of multiplying by 2, I've got to do what? Divide by 2. And I'll leave that out in front like this, a 1/2 sine of 2 theta. Let's put in everything and see if we can't clean it up. That's going to be 49 over 2 pi over 6 plus 1/2 sine of 2 times pi over 6 is going to be pi over 3. Sine of pi over 3, that's a sine of a 60-degree angle. If you're not sure what that is in terms of like, oh, gee, that's square root of 3 over 2, you can take out your calculators and kind of figure it out that way. Just make sure your calculator is in radian mode. So let me clear this out. Calculator's in radian mode, got that. So I want sine of pi over 3. And you're going to get some decimal number. It's going to be 0.866. And if you're looking at that like on, yeah, I got nothing, try this. Hit the square key. And when you square it, all of a sudden, oh, that's 0.75. That's looking familiar. Oh, yeah, that's 3/4. So really what you get when you square it is 3/4. We started out with the square root of that. So I end up with the square root of 3/4, or basically square root of 3 over 2. At 0, both of these terms are 0. So this is pretty much your final answer. 49 over 4 times pi over 6 plus square root of 3 over 4. Nice. Nice. All right, how are we looking on that first one? Just kind of going through and doing some mechanics. A nice reminder on the cosine double angle formula there. Actually, I guess it comes from the half angle formula now, if I think of it right. Is that right? Yeah, I think it's coming from the half angle formula, that substitution that we used here. Nice, nice. Let's move on down to the next one. At least the next one I've got graphed for us. So let's move on down to example B here. For example B, we've got r squared equals sine of 2 theta. I'm trying to remember the fancy word for this. I think it's called a Lemus gate. I'm not sure. Somebody can double check me on that one. But we're trying to find the area of that Lemus gate. Now, one thing they didn't give you is, well, what's the value of r? Excuse me, what value does this go between when you graph this? So we're going to have to spend a little time figuring out, well, where does r go? Or what values of theta will trace this out? So let's take out our graphing calculators for a moment. Now, unfortunately, our graphing calculators don't work with r squared here. So I'll take the square root of this, square root of sine of 2 theta. That's going to be what I'm going to enter into my calculator. Now, of course, to enter in my calculator, I got to do something first. Does anyone know what it is? Change the mode. We want to be in polar mode, not parametric mode or something else. So go down to function, go across to polar, press enter there. So now you're in polar mode. I can hit the clear key to get out of here. Let me clear this button as well, so you can kind of follow along there. Now when I press the y equals key, I get things in R as opposed to, things in X and Y. Let me clear out these formulas here and go back up here, up top, and put in the square root of the sine of 2 theta. Now when you press the X key, instead of a familiar X, because we're in polar mode, you're going to get a theta. And that's fine. That's kind of what we want. It's in our comfort zone. Let's see if we can't figure out where this graph is going to trace out between 0 and, well, 0. So we'll start out with theta equals 0. And we'll have to see when it's going to come back to 0 again. Now my guess for the window, we'll start out at 0. And let's go up to, say, well, we can go up to pi. I think that's going to be overkill. Theta step, for now, just set it at 0.1, like that. So your window is like this. Actually, you know what? For me, I'm going to set it to 0.001. That's because I'm running on a computer. For you, on your graphing calculators, theta step of 0.0 or 0.1 should probably be slow enough that you can see this thing trace out. Now, as far as the other settings are concerned, I don't know where those are going to be, so I'm going to let my calculator figure that out for me. What is it that I press to let my calculator figure that out for me? Zoom 0. All right. So your second favorite thing after Math 9, right? So there we go. So it looks like it's tracing out pretty perfectly, right? Now, if you wanted to square this up a little bit, you could. You could hit Zoom 5. That squares it up so it kind of looks like it's supposed to. But I think that this traces out like we need. Let's hit the trace key. You start out at 0, and you work your way around. And the question is, well, how far is it going to be before I get to get back to 0? And that's going to tell me the limits of integration I have. Now, in this case, I think it actually does turn out to be pi, right? Is it pi? It seems to me like it should be pi over 2 should work. I don't know. You guys could probably trace yours a little bit faster because I had my theta step so small. Are you getting close to 1.57? Is that where it's starting to come back on itself? Clyde?
Yeah, about pi over 2.
Pi over 2? All right. So yeah, what I'm closing in on, the value I'm closing in on is going to be about 1.57, which is pi over 2. And if you think about it, at pi over 2, yeah, I'm pretty close to there. At pi over 2, 2 times pi over 2 is going to be pi. What's the sine of pi? 0. Sine of pi is 0, so it's bringing you back here. So our limits of integration are 0 to pi over 2. I want 1/2 pi r squared. I'm going to write that up here. So area 1/2, not pi r squared, 1/2 alpha to beta of r squared d theta. So I'll put the 1/2 out in front. I've already got r squared. You don't need to take the square root, put it in, and then square it. Just put in sine of 2 theta. D theta. That's already your r squared. How about the antiderivative for that one? What's that going to be?
1/2 cosine theta.
Nice. Yeah, there's a negative in here, right? So let's see here. Because the derivative of cosine is negative sine. And when we run this backwards, we're going to have to take care of that. So it's going to be negative 1/2 cosine of 2 theta, like that. I can bring that negative 1/2 out in front. That's going to be negative 1/4, 0 to pi over 2, cosine of 2 theta. So negative 1/4. Then what? Cosine of 2 times pi over 2 is really going to be cosine of pi. Well, let's see. I'll actually write it out here. It's going to be 2 times pi over 2 minus cosine of 2 times 0 times 0. What happens to the cosine of 2 times pi over 2? Well, it becomes a cosine of pi minus a cosine of 0. And both of those are negative 1, much to my relief. Why? Why is it reassuring that both of those are negative? Overall, when you multiply a negative times a negative, you get a positive. So it's going to be minus 2 times minus 1/4. So we'll end up with 2/4 or 1/2. I can't emphasize this enough. Your area calculations in this section should give you a positive number. If you got a negative number, there's just something wrong. That's it. There's something wrong. You should always be getting a positive number for these kinds of things. Okay, looking good there. Comments or thoughts on example B here?
Can you explain again how you got the limits of integration? That doesn't make sense.
So what I did is I took my calculator out, and when you started tracing, when you put in theta equals 0, you're right here at 0, 0. And then I kept on tracing around until I found the point at which I came back to 0, and that happened when theta was pi over 2. Keep in mind that pi over 2 is approximately 1.57. So when I saw it coming back to around 1.57, I'm like, oh, I think it's pi over 2. You can check it. 2 times pi over 2 would be pi. Sine of pi is 0. So at that point, you have the square root of 0, so the radius has come back to the pole here. All right, good question. Thank you, Ethan. Anything else? All right, let's keep rolling. Somebody's missing a sheet here. There was 2 sheets for the one on the left. So if you're missing one, come on up and get one. Okay, so let's take a look at example C here. And again, we're going to have to spend a little time figuring out what our limits of integration are going to be. Let's do that again on our graphing calculator. I'm going to put in a new function that's going to be 4 plus 3 cosine or 3 sine of theta. So this is a shape of a lemmason. If I had a 4 there, it'd be a cardioid. So 4 plus 3 sine of theta. The difference between this and a cardioid, for a cardioid, that dimple would come back and touch the pole. This one's not. You're going to get that kind of shape when this is a little bit less than this, or if it's just strictly less than this. If these two numbers were equal, then I'd have the shape of a cardioid. Now let's vary this between, let's see what the limits are going to be here. Let's try and think this one through instead of just relying on our calculator. Where is this going to be the largest? Where is this radial distance going to be the biggest? Well, that's when you're multiplying 3 times what value for sine? What's the largest that sine could be?
Pi over 2.
Pi over 2. At 90 degrees, pi over 2, sine is 1. So the largest that could be would be at pi over 2. Pi over 2 for theta. And then you'd have 7 for r. Actually, I think I should put it the other way around. Usually r theta. In any case, this point is going to be at pi over 2. How about this point? what's the smallest that sine of theta can be? Somebody already got the largest. What's the smallest that it can be? Yeah, 3 pi over 2, or if I go the other way, if I just go this way, negative pi over 2, right? Because at negative pi over 2 or positive 3 pi over 2, you're going to be here. Now, I guess the reason I want to go from negative pi over 2 to pi over 2 is because it's one nice continuous interval. Let's see that actually traces out the shape that we expect. Again, you can do that on your graphing calculators. So I'm going to set up my window from negative pi over 2 to pi over 2. And then I'll let my calculator do the rest of the work with the good old zoom fit. So zoom 0. And there you go. It's tracing it out pretty much like we had hoped and expected. We're getting just the right half of that. We can square things up by pressing zoom 5. That looks a little bit more like our figure. Now that the axes are square with each other, they represent the same distance, so you're getting that half dimpled shape of half the figure. So looking good on that. Are you comfortable with how we got our limits here? Pause. Hannah, doing all right there? Okay, thank you. So let's set up the integral. In fact, why don't you set up the integral? I'll give you a few seconds to get ahead of me there. Set up the integral to find the area of just the right half of this limacon. Yeah, you did negative pi. We want to do that
okay.
divided by 2.
Oh, okay.
Now zoom 0, and then hit zoom 5 after that.
Okay. Thank you.
Okay, so our integral should look like this. Should be the area is going to be 1/2 the integral from negative pi over 2 to pi over 2 of 4 plus 3 times sine of theta all squared d theta.
Yeah, when I click the graph, it just like doesn't give me the whole.
It should only give you half of it.
No, like it gives you
Oh,
only half.
you need to set it up from negative pi over 2 to pi over 2.
Okay.
And hit zoom 0 and then zoom 5. Now, this is some more review kind of work here for us. In order to solve this one, I need to square that thing out. So let me do that here. Let's see, I want area is going to equal the integral from 1/2 the integral from negative pi over 2 to pi over 2 of 4 plus 3 sine of theta squared d theta. When you square this one out, let's be careful about this. Let's see here. Remember, a plus b squared is a squared plus 2ab plus b squared. So let's use that idea when we square this out. I'll get 1/2 the integral from negative pi over 2 to pi over 2 of 16 plus how many sines here? Anyone? 24 sine of theta plus 9 sine what? Squared theta. Well done. d theta. Now, unfortunately, we don't have, well, I guess there is some formulas for it, but it's not something that I have memorized. What we're going to do is we're going to use that half angle formula again to kind of work our way around having a sine squared. Sometimes they're called power reduction formulas because we're going to go from a sine to a cosine, or sine squared to a cosine. So it's going to be 16 plus 24 sine of theta plus 9 times 1 minus cosine of 2 theta over 2 d theta. If we distribute the 9, I'll get a 9 halves added to 32 halves is going to be 41 halves. So let's clean this up a little bit. That's going to be the integral from negative pi over 2 to pi over 2. I'm just adding up the constants here, which is going to come from these terms. So it's going to be 41 over 2 plus 24 sine of theta minus 9 cosine of 2 theta, all d theta. Okay.
That would be 9 over 2 cosine 2 theta, right?
Yes. Thank you. Yeah. Now, if you're really clever, you'll notice that we have a symmetric interval and an odd function. So this part is just going to turn to 0. I don't think that's something a lot of you are going to catch on the fly, so let me just work that through. So it's going to be 1/2 negative pi over 2 to pi over 2 of 41 over 2 times theta minus 24 cosine of theta, and then minus 9 over 2 times sine of 2 theta divided by 2. And those 2's can combine and make a 4 if you'd like. That's fine. There's just a mountain of yucky algebra here in front of us. Let's see. So we're going to get 1/2 of 41 over 2 times pi over 2 minus 24 times cosine of pi over 2. There's good news about cosine of pi over 2. What is that good news? 0. So that's a nice 0. And then I'll have minus 9/4 times sine of 2 times pi over 2. Two times pi over 2 is pi. What's the sine of pi? 0. So we're lucky on that first part. Let's take a look at what happens on the second part. When we do our lower limit, that's going to be 41 over 2 times negative pi over 2. By the way, we're subtracting all of this. Minus 24 times cosine of negative pi over 2. And I've kind of run myself out of room here. Minus 9/4 times sine of 2 times, again, negative pi over 2. And we got some more nice simplification, right? That turns to 0. That turns to 0. So basically we're getting this quantity twice times the 1/2. Clean it all up, you'll end up with 41 pi over 4. Whew. A lot. A lot of messy algebra arithmetic on that last one there. Whew. Okay. A lot going on there for example C. Right now, this is just a good reminder of some of our work with polar equations and some of the tricks we had for integration. But I want to dial it back for a second and take a look at the actual, what's going on, how these things are getting calculated. Before I do that, is there some details here on example C that you're not sure about? James?
So with the negative pi over 2 and then pi over 2, you want to split those up? Like, to make a 0 to pi over 2?
You can do that if you have an even function. Yeah, if you had an even function, then yeah, you could double it and go from 0 to pi over 2. But this is an odd function. Let's see, is that an even function? Back up here. This is an odd function, so we really didn't need to play with that one. And this one, that's an even function. Maybe we could have done something there to help us out. But in the end, it wasn't too bad because all they turned into was 0. So keep in mind, a lot of times, most of what I'm interested in you is getting this set up. I mean, getting that set up right is a big part of this. So, yeah, good question. Yes?
How do you know it's even or odd?
So an even function would be stuff that's symmetric with respect to the y-axis. And an odd function has what's called origin symmetry. I have a demonstration about that someplace. I'd like to show you, but I can't put my hands on it right now. But remind me sometime, and I'll bust it out and try and show you. Just kind of a quick look at that, maybe. Let's see, Desmos. So graphs like y equals cosine of x, those are symmetric with respect to the y-axis. So that's even symmetry. If you had a graph like y equals sine of x, that's got odd symmetry because when you look at the line y equals mx, where this intersects our graph, it's always symmetric points on opposite side of the origin. So when I click this point here, notice that they're mirror images of each other, just on opposite sides of the origin. And the nice thing is if you integrate an odd function over a symmetric interval, it's 0. Because what happens is that you've got, just take a look at this one here. If I was integrating from here to here, when you integrate from negative 2.4 to 0, you're getting some area, but it's a signed area. It'll be negative. And then over here on the other side, you're going to get that same area, except positive. When you add those two things together, they annihilate each other. So you get 0. So if you can see that, for instance, like right here, that sine is an odd function, then you can say, oh, well, that part's just going to be 0 right away. It's nice. I mention it for those of you who can kind of catch that on the fly, but I wouldn't stress on it too much because you're not always going to have symmetric intervals like that. But if you do spot it, that's great. Great. Anything else? Okay. Let's actually take a look at one of these things kind of up close and personal here. So the cool thing is if you got a QR code and you're watching this later, you can dial up this link here, which is nice. In any case, what do you think when you look at this graph? Does that look like a circle? Yeah, it looks pretty close. And in fact, if you follow the link, then I think it's this one right here. So the orange graph is the graph of a circle, and the blue graph is our actual graph. So they're very close. Now, one of the nice benefits of polar equations and graphs in polar is that a lot of times they're much easier and simpler to work with than the corresponding graphs in rectangular coordinates. So for this one in particular, I played around with a little bit to change it back into rectangular coordinates. So the first step you would do is you multiply everything by r. That way you can have some substitutions. This is going to be your x squared plus y squared. There's going to be a y. That's going to be 4 times the square root of x squared plus y squared. Move this over to the other side if you want. You still have kind of an ugly equation, right? If you wanted to get rid of that square root, you'd have to square both sides, and squaring that would be a real mess. There's just no way to make this a pretty formula. It's just an ugly formula. But check out how easy it is in polar. It's not bad. So polar definitely has a place for our work here. It's just that sometimes it's a little different working with polar. We're going to have to think a little bit different, but we'll do that. All right, let's see. Let's shut that off. Let's work on finding the area there. So this is example D. So we got to figure out, well, what values of theta are going to trace this out. Do I go from 0 to pi over 2, 0 to pi, 0 to 3 pi over 2, 0 to 2 pi? What values of theta are going to give me one lap around this figure? So in as much as sine has a period of 2 pi, that might be a good guess to start with. Let's just kind of check it out. So I'm going to go back to my equation editor, put in a new equation, 4 minus sine of theta and now I'm going to set my window from 0 to 2 pi. What's the next step? Your second favorite key on your calculator now. Zoom 0. Yeah, zoom 0. All right, so looking good there, zoom 0. Now our equation, our graph's not going to necessarily look like what we had on our sheet there, is it? It's like, well, wait a minute, that looks like an ellipse. That's because the width and the height are different scales. To scale that up right, you can follow it up with zoom 5. And now that should look a lot better. Should look a lot closer to what we have on our paper. It's looking good there. And 0 to 2 pi does take us all the way around and complete that figure. So 0 to 2 pi is going to be enough. Let's just set up this graph here in terms of the integral to find this area, and then we'll kind of fast forward to the happy ending because I want to spend some more time on some of these other equations. Let's see what you can do. 1/2 integral of what to what?
0.
All right. So good. Our limits are 0 to 2 pi. What should I put in here for the integrand?
4 minus sine theta squared.
Liz, do you agree with that?
Yeah.
All right. 4 minus sine theta. The whole thing squared, d theta. Now this is another one where you're going to have to use that power reduction formula. Yada, 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 etc. Let's try a little experiment here. Let's remind ourselves of our favorite function on our graphing calculator, which is Math 9, right? So let's go back to our calculator and see if we can't figure out exactly what value this is. So a little hocus pocus here coming up. So I'm going to put the 0.5 out in front of my integral, and then Math 9, integral from 0 to 2 pi. Make sure your calculator is in radians. I don't think this would work if your calculator wasn't in radians. You're going to need a double set of parentheses. Parentheses, and then parentheses again. 4 minus, oh gosh, and here we know, we need parentheses again. Your calculator does not understand the sine squared that you and I might write in our notes. So parentheses, sine theta, parentheses to close out the theta, parentheses to close out the sine, and then another parenthesis to close off the binomial. Let's see, do I have that? No, I guess I do. Was it 3 left parentheses, 4 left parentheses? I need, let's see. That one, no. I need one more parenthesis. I guess I gave myself an extra set of parentheses. No, I didn't. I got to hit the square key here.
Yeah, it's not just
No.
sine squared though. So.
Yeah, no, you're right. I got to square the whole thing. So let's clean this up a little bit. I think I've got an extra set of parentheses around sine of theta that I don't need. Right parenthesis, and then the squared key. So now if you take a look where this squared is, it's squaring that whole term, 4 minus sine of theta. And you've got to tell it d theta. I kind of like that. It's nice that the Texas Instrument did that. And bam. Now that's looking kind of ugly. You might not have any idea what it is. I don't have any idea what it is. But I'm going to try this. Let's divide that. Let's divide out the pi. Because I'm guessing that there's going to be a pi in here someplace. So if I divide that by pi, oh wow, I get a pretty nice answer, don't I? What answer is that? Well, let's hit the math key. 33 over 2. Okay, so the answer that we need here then, the exact answer is 33 over 2 times pi. Yay. Pretty nice. You got an exact answer. All right. Nothing wrong with checking your answer that way. If I want you to finish with FN int, that's a little bonus point if you can give me an exact answer by doing something like that. Okay. Let's take a look at example E here. How are we doing on these so far? These okay? Yes? That's easy? All right. Joseph? Thank you. All right. Let me kind of give you a little bit more perspective on what it looks like when you're integrating these things. So if you're following along on the website, you can click on the graph for E and then slowly dial this up. And what's going to happen is it's going to trace things out kind of the way you're sweeping it out with all these different sectors. And it's sweeping out that area in a radial way as you go around from 0 to 2 pi. So pretty nice. Pretty nice. But you're just, like I said, you're just sweeping out those rectangles or those sectors one at a time, add them up in the form of a Riemann sum, and that Riemann sum becomes a Riemann integral. Because these two things match, you get that nice little point there. That makes us a cardioid. So enjoy the most romance that math has to offer here. Set up the integral to find the area bounded by this. Finish with FN int. Go ahead, see what you can do. I'll kind of pause. So if you're watching this later, then try and race through to the end. My pause button. Hey.
Oh my gosh. Wake up, wake up. I was watching it last night. Oh, yeah.
Can you finish it up longhand?
All right. So we're going to take the area is going to be 1/2 the integral from 0 to 2 pi of 2 minus 2 sine of theta squared d theta. You can play the same game we did last time, so that as we can integrate it with fn int, divide out the pi, and you should get a 6 if I'm not mistaken. Math 9. Let's see, 0 to 2 pi. And I forgot that factor of 1/2, so I'll put it in my integrand. 0.5 times parentheses 2 minus 2 sine of theta. Let's see, sine of theta. There. Another parenthesis. Make sure these parentheses are balanced. So this parenthesis and this one close off that 2 minus 2 sine of theta. I want to square that, and then d theta. If you divide out by pi, you should get a nice 6. So that tells us that this is actually equal to 6 pi. Very nice, very nice. A couple more here. One of them I'm going to leave for you to do at home because I want to look at example G here. Maybe we can get to example H as well. So let's take kind of a quick look at example F, and you can kind of play around with this at home as you like. So you're asked to find the area inside of these two curves. One of the things you're going to need to do is you're going to need to figure out, well, where do these curves intersect each other? So, okay, that's something we're going to spend some time on with example G. But let me show you kind of graphically speaking what's going on with some of that. So let's shut off this one and turn on this one. So here's your graph. And I want to find where these curves intersect each other and what area I'm going to have to sweep out. Now keep in mind the way your area is swept out. It's swept out from the origin to the curve, and it's swept out in terms of sectors. So I've divided this up into a few sectors here so we can kind of see what's going on a little bit better. If you drag this first cursor, you can see that the area that's being swept out is between the pole or the origin and this figure right up until we get to this point, which is pi over 12. And then to continue working on the inside here, well, now I need to sweep out the area between the origin, and the circle. And I'll do that all the way up to, I get to here. And then what? Now I got to start working with the area between the origin and this figure again. So this can be this last part right here. So if you looked, I had to split this up into several different integrals depending on the value of theta and where you're at. Now, one other thing here. This area really gets doubled, right? Because this figure is the same on one side of the origin as it is on the other side of the origin. So eventually you've got to double it. So we found our points of intersection. You have to set up a couple integrals, and a couple of these get doubled. So a lot of thought here. This is kind of a really bare bones proof of this answer. One thing you should notice is that this total should be positive. It is positive, but you want to double check that it's positive when you're all done just to make sure. So spend a little time with that. See if you can explain it to, your brother or your sister or a chair. Border collies are pretty smart. They probably latch onto this really good. So find the captive audience and see if you can explain some of these steps here. Why do I have a 4 here and a 4 here instead of, a 2 or 1/2? Those kind of questions. Okay. Let's see. Let's turn our attention to example G here. Example G's got a different graph. Let me fire that one up here. Let's shut off all that. Where's here? Example G. I love these clover shapes. So you get that clover shape from the sine of 2 theta, that graph. And, well, it's going to intersect our circle at a couple points. Now, unfortunately, in Desmos, you can't click these points as you can for Cartesian coordinates. In Cartesian coordinates, x and y, we can say, oh yeah, let's just click that and find those points. We can't do that. We're going to have to manually find these points of intersection here, and that's going to be our first task, is to figure out where that happens. And where I envy you is you get to work with some trigonometric equations, which I know you're just all really giddy about. So I can see the smiles on your face. You're like, oh yeah, it's been so long since I've done these. Thank you, thank you. So let's take a look at this. We've got 2 equations. So this is example G. We've got r equals sine of theta and r equals sine of 2 theta. So this is a circle with a center of 1/2 on the y-axis. This is that 4-leaf clover thing. You might remember the other day we talked about this a little bit. If you put even numbers here, you're going to get twice that many number of petals on your figure. So if I put a 4 in here, I'd get 8 petals. If I put a 12 in here, I get 24 petals, and so on. Our goal is to figure out where these radii coincide. Where do they cross each other? So you're going to do this. You're going to set sine of theta equal to sine of 2 theta. And you look at that with despair, you're like, oh, wait a minute. How am I going to get theta by itself? What am I going to do? Well, what you could do is remember the sine double angle formula. What's the sine double angle formula? Does anyone remember that one? 2 sine theta cosine of theta. Nice. It's helpful in a lot of these problems to have 0 on one side so we can start using the 0 property of multiplication. Sine of 2 theta, or 2 sine of theta cosine of theta minus sine of theta, like that. Or 0 product property, I guess I could say. If you notice, I've got a sine of theta in both of these terms. I'm going to factor that out. I'm turning this deliberately into a product, so I have sine of theta times 2 times the cosine of theta minus what? Minus 1. And this is what I wanted. I wanted to know, well, where is this happening? Where does that actually equal 0? So one possibility is when sine of theta equals 0. The other possibility is when 2 cosine of theta minus 1 equals 0, which is cosine of theta equal to 1/2. And then you have to do the inverse cosine. Inverse cosine of theta, or excuse me, inverse cosine of 1/2 actually gives you two possibilities. There's two places where this will cross, or the x coordinate would be at 1/2. One of them is at pi over 3, and the other one is 5 pi over 3. And then over here, sine of theta equals 0 when theta equals 0 or theta equals pi. Okay. So we've got several points of intersection. We can plug in these values or these angles at pi over 3. I guess I could get 2 pi would be one as well. We can fill in our points of intersection and go from there. Let's see. Bless you.
Thank you.
I think that's actually all they're asking for, though, is find the points of intersection. So let's kind of limit that. Now I've limited this. All right, I guess we can't use 2 pi because I'm assuming that theta is less than 2 pi. So we'll have to scratch that one out of our solutions, like that. But we do get theta equals pi as a solution, theta equals 0 as a solution, and a couple more here and here. Let's find those coordinates for the points of intersection. So I'll make a little list here. Let's do a little chart. Theta and r. When theta is 0, r is 0. When theta is pi, r is 0 again. When theta is pi over 3, at pi over 3, you're going to get square root of 3 over 2. And at 5 pi over 3, you're going to get negative square root of 3 over 2. So these are your points of intersection. That's all they're asking for in this particular problem. Okay. Not bad, not bad. So a quick little review of some of your trig. I think that's all I'm going to take the time for this section right now. Are we okay with our little trig review there? All right, appreciate that. Let's put this section to rest.